Chapter 5, Disinfection. Now, of all the questions on the test, all of them are going to be addressed inside of the handbook. So, like we talked about earlier, this exam is open book and open note. But, like I said, 99% of the actual questions in the test are addressed in the book. What you're seeing here on the screen is the answer to the question, the single question that is not addressed in the book. And it talks about the two things that are required in order for a chemical to be considered a disinfectant. Because of this, I highly recommend that you write this down, that a chemical must kill or inactivate 99.99% of contaminants and leave a residual in the water to be considered a disinfectant. Again, 49 out of the 50 questions on the test are addressed in the book, except for this one. So make sure you pause this video and write this down. And now that we've talked about what is required of a disinfectant to be considered a primary disinfectant, let's explore these a little bit more further. Now, one of the big things that you're going to see out here used is chlorine. Chlorine is our most common type of disinfectant. The way chlorine works is when chlorine is introduced into the water, that chlorine is actually going to release something called hypochlorous acid. It's that hypochlorous acid released into the water that actually goes to the killing or inactivating of the various pathogens and algae inside of our water. Now, there are three different types of chlorine that we use in the industry. The first is gas chlorine. The second is liquid chlorine, and the third is our solid chlorines. Now, it's always good to know that chlorine is naturally gaseous, so it's always trying to convert back into that lowest common denominator of a gas chlorine. Now, another thing to keep in mind is that our pH and our hypochlorous acid are interdependent of one another. It means that, as you can see on the slide, the lower the pH goes, the higher our hypochlorous acid, or more effective our hypochlorous acid is. So as a result of this, the lower the pH, the more effective the hypochlorous acid. But obviously we can't operate our pools at a 6.0 pH, otherwise we're going to risk burning the flesh off of the people inside of our pools. So we want to have a good balance, and that balance is found in that 7.2 to 7.8 range. This is given to us by our health department as a good operating range for our chlorine in conjunction with our pH. As you can see, a 7.2 pH is going to have a 66% hypochlorous acid production range, all the way up to 7.8, which is at a 33%. Now, obviously, we want to keep it closer to that 7.5, which is a 50% hypochlorous acid range, because 50% is way better than 33%. But we also want to keep in mind that our pH affects our swimmers' comfort as well. And at that 7.5 pH, we are looking at the pH of the human tear. 7.5 is the pH of the human tear. So if we keep our pH at 7.5, our swimmers will be able to open their eyes under the water and have no issues with itchy or watery eyes as a result. We also have the benefit of a 50% hypochlorous acid production at that 7.5 pH. So 7.5 is considered a perfect pH, with a range of 7.2 to 7.8 pH being the range that our health departments give us and allow us to stay open as long as we're within those ranges. Now, the way our chlorine is allocated is roughly 75% of our chlorine goes directly towards water clarity. Now, for me, I have used literally about 5 bottles of clarifier in my 24-year career of working on pools and spas when it comes to clarification of the water. The reason why I've done this is because water is clarified way easier with chlorine. So keep that in mind, that we're not always going to need to run to our clarifiers when it comes to water clarity, because our chlorine is going to do the job better than the majority of our clarifying agents out there. As you can see, 25% of that chlorine allocation goes to the killing of the pathogens in the water, the bacteria, the parasites, the viruses, algae, so on and so forth. Now, when it comes to chlorine readings, the vast majority of us are using what's called the Taylor test kit. Now, that Taylor test kit is a blue box, and inside there, you've got all your various tests that you're going to use to figure out what the chemical levels are inside of your swimming pool. Now, when it comes to chlorine, you're going to get some various different readings in there. Now, with our chlorine readings, we're going to have our free chlorine, which is our first reading. Now, our free chlorine is our available disinfectant. Free chlorine is good chlorine. The way I like to remember this is we all like free stuff. Free stuff is good stuff. So free chlorine is good chlorine. Now, we want to maintain these levels at between 3.75 and 4.5 parts per million. The old numbers used to be between 1 and 3 parts per million, but our latest research is showing that if we keep our chlorine levels closer to that 3.75 to 4.5 parts per million, we're going to see better health and safety inside of our facilities. We can go down to a minimum of 1 part per million on those pools and a maximum of 5 parts per million. Now, again, you're going to want to check your local and state codes to ensure that you are making sure that your free chlorine is within acceptable parameters for your district, for your city, or for your state, depending on where you're located. Now, the next reading that we're going to be looking for in our Taylor test kit, in fact, in any of our test kits out there, is something called our combined chlorine. In the previous chapter, we talked about what combined chlorine is. Essentially, it's dead chlorine. When a free chlorine floats through the water, finds a contaminant, it combines itself to that contaminant and basically gives its little chlorine life up for the sake of killing off that contaminant. It then becomes a combined chlorine. Dead chlorine, useless chlorine. It's not an effective disinfectant. Once that combined chlorine evaporates out of the water, it creates that combined chlorine smell. We don't like combined chlorine in our water, so we need to make sure that we're testing it regularly to make sure we're keeping those levels down. Simply because these are a skin and mucous membrane irritant, and they're also a pulmonary irritant now. Now, eradication is ideal, and we're going to talk about that a little bit later on in this chapter, how you eradicate that chlorine. That combined chlorine. Now, next we're going to talk about total chlorine. Now, total chlorine isn't an actual chlorine. All total chlorine is the reading when free and combined chlorine readings are added together. The reason why I bring this up is because the vast majority of our test kits won't directly test for a combined chlorine. Instead, what they're going to do is they are going to add the free chlorine and the combined chlorine together into a reading called our total chlorine. So what we need to do as operators is we need to kind of sleuth this. What we're going to do is we're going to take our total chlorine minus our other chlorine reading that we can actually take in the pool, which is our free chlorine. So we're going to take our total chlorine minus our free chlorine, and whatever's left over is our combined chlorine. So these are the 3 readings that we're going to be looking at every single time we test our water for disinfectant. Now, when it comes to chlorine and UV exposure, we're going to be talking about stabilized and unstabilized chlorines. Now, unstabilized chlorines mean that these chlorines are prone to UV light degradation. An unstabilized chlorine is prone to UV light degradation. What does that mean? That means that sun shining down on your pool is actually going to automatically degrade that chlorine level. In fact, certain studies show that after 1 hour of UV exposure from the sun, our chlorine has broken down by 50%. That's pretty crazy numbers from our unstabilized chlorines. Now, you'll see your unstabilized chlorines on page 52 in a chart are sodium hypochlorite, calcium hypochlorite, and chlorine gas. Now, like I said, on page 52, your chart may look like this, or it may look a little bit different depending on the edition of the book that you're working with, but the information is still solid, still reliable, and it matches through any of the editions. Now, let's go ahead and first figure out what these columns are all talking about here on the left side. On the left side here, you're going to see a bunch of different information. Now, the big one that we're going to be looking at is the active strength. The active strength says that is the amount of chlorine in the product itself. The rest of the ingredients in there are non-hypochlorous acid producing products. So when we look at the active strength of these chemicals, we'll see that that's the actual amount of chlorine inside for use on killing whatever the pathogens are inside your water. Below that, you're going to see our pH in a 1% solution. Now, here's the thing that I want you all to remember. This is very important that you remember this, that every single time we add chlorine to our water, it's going to affect our pH. Each one of our chlorines has a specific pH that it measures in at, and when we add it to our water, it's going to potentially throw off our pH balance as a whole inside of our water. There's also going to be a question that asks about raising or lowering of the pH and what kind of chlorine does that on the exam, and this is going to be the section that you're going to look at. So make sure that you take a note of page 52. Right below that, you're going to see the pH effect in the water, whether this chlorine is going to raise or lower the pH simply by adding that chlorine. And then finally, we have our physical appearance at the bottom there. Physical appearance shows us exactly what this chlorine looks like when we get it delivered. So let's go ahead and go down this list here, and first we're going to talk about sodium hypochlorite. As you can see, it has an active strength of 10 to 12%. So what does this mean? Well, essentially 88 to 90% of this product is something other than chlorine. That's pretty rough. So what we need to remember is with all of the downfalls that we have with certain chlorines, we're also going to get some major benefits, and vice versa. For all of the great benefits you get with a certain chlorine, you're also going to get some downfalls. Now, some of us will look at this and say, well, that's a downfall that it's only 10%, sometimes even 8%, depending on where I'm purchasing from. And as a result, I'm paying for chlorine or for a product that isn't all chlorine. Now, let's look at the physical appearance here. It's a liquid, so this gives us an insight as well. What we can see is that 90% of this product is water, 10% is chlorine, and 90% is water. Essentially, what we're looking at is a diluted bleach, is what sodium hypochlorite is. Now, the reason why I say there is a benefit here is because it is liquid. For those of us who are using our automatic feed systems that are using liquid chemicals, you'll be using liquid chlorine inside of those systems. So, for the fact that we're going to get a lower active strength out of this, but get the versatility of automation, that's huge. Our sacrifice is low strength. Our benefit is extremely versatile addition possibilities. And now let's look conversely at the calcium hypochlorite. We're up to 78% chlorine active strength there. That's great. Well, now let's look down at the physical appearance. It comes in a granular form, a tab form, and a briquette form. Now, with calcium hypochlorite, the vast majority of us are going to be working this or with this in the physical appearance of granular chlorine. Granular chlorine. What we need to remember is with granular chlorine, the only way to add this to your pool is to go out by the side of the pool, grab a bucket full of water, get your granular chlorine, pour it into the bucket, stir it up, and then pour it over the deep end of your pool. Now, this works, but what we need to remember is we can never add chemicals into our pool during open hours. We can never add chemicals directly to our pool during open hours. So for those of us who in the middle of the day are going to be testing our pool and we see that our chlorine's low, we can't use calcium hypochlorite in granular form to boost our chlorine levels. So this is where we get the downfall or the sacrifice with calcium hypochlorite. The benefit is that active strength. Now, for some of us, we may be using what's called a pulsar system. With the pulsar system, it uses calcium hypochlorite briquettes. And these briquettes get a little splash of water sprayed over the top of them. That water runs down through the briquettes and then chlorinates the water inside of your pool through this briquette system this way. That's a great system, but it's not available in all regions and it's not widely used. So remember that the majority of the time that we're using calcium hypochlorite, we're using it in the granular form. And as a result, we are hindered from using this and introducing it to the water whenever we want to, simply because we cannot do it while there are people swimming inside of our pools. Next, we have lithium hypochlorite. Lithium hypochlorite is no longer available in the United States. So, with that one, we're just going to pass right over it. Then we're going to talk about our last unstabilized disinfectant or unstabilized chlorine, which is chlorine gas. Now look at these numbers. 100% active strength, a 0 pH. This is pure acid, essentially. And look at our physical appearance. It is gaseous. Chlorine gas is extremely effective at killing everything, including us as operators. So we want to make sure that if we're using gas chlorine, we are being as safe as possible. So to put it into perspective, it only takes 35 parts per million of chlorine gas in a room to essentially and effectively kill a human being. So let's fill a single room. Let's fill the room up that you're sitting in with 1,000,000 marbles. We take out 35 of those marbles and replace those with chlorine gas marbles. That's all it takes inside of that room to kill off a human being. So this is why people are going away from the use of chlorine gas, which we should all be thankful for. Now next, let's talk about our stabilized chlorines. Now stabilized chlorines mean that these chlorines are safe or protected from the effects of UV light degradation. These stabilized chlorines, as you'll see on page 52 on that chart, are trichlor and dichlor. Now, let's talk about stabilized chlorines, because it sounds really good in the outset. But when we get into the gritty details of what's involved with trichlor and dichlor, we might not be as excited about using these. Now, for many years, we used our unstabilized chlorines, and the sun was destroying these things. So, science came up with a solution to add something called cyanuric acid. Now, cyanuric acid will also be known as a stabilizer or a conditioner or a protectant or a sunscreen. There's a bunch of different names that are used to describe cyanuric acid. And the concept is it creates a protective coating or shell around our chlorine that serves as essentially a protectant from UV light degradation. Now, it's really good to have all of the information up front because it's very important that we remember that cyanuric acid doesn't completely protect our chlorine. It only slows down the degradation process by about 3 to 4 times. So it's going to allow your chlorine to last a lot longer in the water, but it's also going to cause a myriad of problems along with it. We want to keep these levels below 10 to 15 parts per million. General consensus out there is 30 to 50 parts per million. But once we talk about the downfalls of cyanuric acid, you'll see why we at Pool Training Academy recommend that we keep those levels below 10 parts per million if we're even using this at all. Now, what's going to happen is as we add cyanuric acid to our water, it's going to begin to trap the effectiveness of our chlorine. Now, the place that we're going to see cyanuric acid used by far the most is going to be in our trichlor 3-inch tablets. Our trichlor 3-inch tablets. Those are the ones that we put inside of our rainbow towers, inside of our pump rooms, that deliver our chlorine through that tower. Now, with this trichlor, essentially what we're doing is not only are we adding chlorine to our water, but we're regularly adding more cyanuric acid to our water as well. And once we get above that 25 parts per million of cyanuric acid, science has shown us that it starts to hinder our chlorine and its effectiveness significantly. The more cyanuric acid that you add to your pool or your hot tub, if you're using chlorine inside of your hot tub, the more likely it is to trap and hinder that chlorine from being used. For instance, I showed up at a property a couple of years ago, and when I got there, the water was the color of split pea soup, just super dark green. So I tested the chemicals, and believe it or not, the chlorine levels inside of this pool were 5 parts per million. Because I know about cyanuric acid, that was the first place that I looked for the response or the possible culprit for this problem. And sure enough, the cyanuric acid levels were 250 parts per million inside of this pool. As a result of these high cyanuric acid levels, the chlorine was trapped behind that wall of cyanuric acid, and it could not kill the algae in this pool. So again, making sure that we keep our cyanuric acid levels are low are really crucial to making sure that our pools still look good. Another thing to keep in mind is over time, we've started to discover that given enough time and the right circumstances, cyanuric acid can actually convert over into cyanide inside of your pools. So we want to make sure that we're avoiding anybody swimming inside of a cyanide pool. It's not a great marketing tactic to say now featuring cyanide inside of our pools. So this is why I also recommend that you limit your cyanuric acid use or get rid of it altogether. Because the last biggest issue is if I do want to lower my cyanuric acid levels, there's only one scientifically proven method to do that, and that is to drain your pool and completely refill. To drain down and completely refill with new water. So needless to say, I personally am not a huge fan of cyanuric acid. We're starting in the industry to move away towards cyanuric acid, but still the vast majority of sales entities out there are going to try to push you towards cyanuric acid. Now, again, the reason why people like cyanuric acid is because if you look at these trichlor numbers, they're pretty darn high. They're in 99% active strength zone, which is great. But again, like I said, the downfalls that you're getting with using that cyanuric acid is going to be, in my opinion, not worth the active strength numbers on something like this. Now, there's other alternatives for just traditional chlorine, and that's to generate our own chlorine inside of our pools. That's right, chlorine can actually be produced through introducing electrical charges to salt. Chlorine can be produced through introducing electrical charges to salt. This is called electrolysis. And there's two different forms of electrolysis. The first is our inline process, and the second is our brine process. Now, as you can see on the photo here, what we're going to do is we're going to dump a bunch of bags of salt into our pool itself. We churn that up, mix it up, and it runs through our system. And once it hits this little conversion cell here, this is where that electrical charge is introduced, and on the other side, it produces out liquid chlorine, or sodium hypochlorite. That sodium hypochlorite goes out into the pool and starts the disinfection process. Now, a couple of things to keep in mind with this. There's a lot of confusion around salt pools. First and foremost, it's not the salt that's doing the disinfection inside of your pool. It's actually the converted salt into chlorine that's doing the killing inside of that facility. That's one of the biggest things you'll always hear out there is people believe that the salt itself is disinfecting the water, but that's not true. It's the converted salt that's been converted into liquid chlorine that's doing the killing. Another thing you'll hear about this is horror story after horror story about how their salt system destroyed their pool. And I have no question, or I should say I have no qualms with the fact that they probably did get their systems destroyed. But the reason why they got their systems destroyed was not because of a salt system, but because they didn't take the proper precautions to protect their pool from the byproducts and the aftermath that can come from an unmitigated salt swimming pool. What I'm talking about is the addition of something called an inline anode. This is a sacrificial inline anode. And what it does is it protects all of your equipment from salt system degradation. As you can see in the image, inside of this little device is a little disc, and it's made out of copper. This is installed inside of your line, and as water runs through it, it takes all of those harmful total dissolved solids that are created by the salt byproducts, and those total dissolved solid byproducts start attacking that copper disc inside of this anode first and foremost. Over time, you're going to see that anode be literally eaten away, and you're going to have to replace that copper disc over time. But what this is going to do is it's going to prevent any of that scale buildup from affecting your copper heat exchangers, and it's going to save your system a lot of degradation, or overly aggressive degradation. So making sure if you have a salt system that you're adding an inline anode is absolutely crucial for you. Now, the second process that we're looking at is called the brine process, or the brine method. Now, what happens is we take a separate tank, we fill it with water and salt, and we mix that all together into creating a brine. That brine is then passed through a conversion cell and dripped out on the other side as a sodium hypochlorite or liquid chlorine into your water. Now, these are just two of the possibilities, like I said, the most popular possibilities when it comes to our salt systems. And as long as you're installing these well, they work really well as in addition to a regular, I should say, as an alternative to a regular or traditional chlorine system. Now, next, let's talk about bromine. Now, bromine is chlorine's cousin, and instead of releasing hypochlorous acid, bromine releases hypobromous acid. Now, it's good to remember that at a 7.5 pH, bromine is actually 92 to 96% effective, compared to chlorine at a 7.5 pH, which is at a 50% hypochlorous acid production. So, bromine is significantly more productive at the same pH than chlorine is. Now, another thing that's really interesting is our bromine tabs are actually infused with chlorine. And the reason why we do this is because when free bromine floats through the water, it will attach itself to a contaminant and become a combined bromine. But when you introduce chlorine into that combined bromine, it's actually going to re-kickstart that bromine into an active bromine again, an active free bromine, that is. So not only is bromine a stronger disinfectant than chlorine at the same pH, but it also goes longer than chlorine. Now, remember, it's not protected by cyanuric acid, but one of the big reasons why we love bromine in our industry is it's more temperature stable than chlorine. It's good to remember that at 84 degrees, chlorine will convert back into a gas. So if I'm using chlorine inside of a hot tub, and my hot tub's at 104 degrees, I'm gassing out the majority of my disinfectant. Now, bromine, since it's liquid in nature, is going to be more temperature stable and going to hold out a lot longer and a lot better residual inside of our hot tubs than something like chlorine would. You'll see the numbers for bromine on page 52 in that chart as well. Now let's talk about something called secondary disinfection. Now, secondary disinfection is exactly what it sounds like. It cannot be used as our primary source of disinfection. The reason why is, as you see here on ozone, it does not maintain a residual in the water. Now remember, on our first slide in this chapter, we talked about the two requirements for a disinfectant. It needs to kill 99.99% of contaminants, and it also needs to leave a residual in the water to be considered a primary. Ozone will kill 99.99% of contaminants, but it will not leave a residual in the water. As such, this can only be considered a supplemental disinfectant. It can only be supplemental. We always go back to our chlorine first and foremost, because if somebody jumps into the water with a communicable disease or illness, that chlorine needs to be in the water itself in order to be able to kill off that illness at the contact point. So ozone is really, really good when it comes to killing off a wide range of pathogens, as is UV or ultraviolet light. But again, our UV and ozone do not maintain a residual in the water, so they need to be considered a supplemental oxidizer or disinfectant. Now, one of the big things to remember is both of these systems work really well when it comes to a backup or a more powerful backup disinfectant, but they do come at a price. UV needs to have its bulbs replaced every 10,000 hours roughly, and that can be a pretty hefty price. Now with our ozone generators need to be replaced every once in a while as well, and that comes in at a pretty decent price tag as well. So with ozone and UV, who should be using these? Ideally, we should have these on all of our pools and spas if possible, because the more disinfectant we have out there to use, the better. But for people who are on a budget, I highly recommend that those who are working with higher populations of kids, people with compromised immune systems, or those who are in the elderly range, set up a UV or ozone system inside of your facility to protect those people from any potential pathogen release that could happen and affect them more significantly than the rest of the population. Now, before we move on to chemical adjustment, one last thing that I want to talk about is something that's fairly brand new to the market, and it's called the AOP, or Advanced Oxidation Process. Essentially, what AOP does is it takes the best of both ozone and UV, and it uses them to kill off a wide spectrum of illnesses inside of the water. If you want more information on AOP, just do a quick Google search and you'll get all the information that you could possibly need on converting your system over to a supplemental AOP system. Let's talk chemical adjustment. Now that we understand about our chlorine, let's understand how to adjust chemicals in certain situations. So go ahead and turn over to page 6 and 7 in your workbooks. Go ahead and turn over to page 6 and 7 in your workbooks. Now on page 6, you're going to see all of our chemical adjustment increases. All of our chemical adjustment increase rates is what we call these. You'll see our to increase chlorine section, to increase total alkalinity, calcium hardness, so on and so forth. And then over on page 7, you're going to see our 2 example questions. Then you're going to see a long list of our formulas that you can use during this online portion and during the exam itself. And also remember at the very bottom there that our answers must be converted to pounds or gallons. Now, inside the test question, or I should say the formula itself, we do have the conversion section there, but you must remember that all of our answers need to be converted into pounds or gallons. We have those conversion numbers right there in front of you. Converting ounces to pounds, we're going to divide by 16. Converting fluid ounces to gallons, we're going to divide by 128. So let's go ahead, break these down, and work through it together. So you're going to see our first question says that our pool is 55,000 gallons. After testing, your results show your free chlorine is 1 part per million. How much calcium hypochlorite would you need to add to reach 3 parts per million? So it gives us a lot of stuff, and we may be a little bit confused by that. But the good news is the formulas that you find on page 7 are going to walk you through how to adjust this. The way that we adjust our chemicals is we're going to take our pool volume divided by 10,000 times our parts per million change requirement times the chemical addition rate that we're given divided by our conversion. We do that math all the way across and we'll figure out our answer. So in this situation, it's basically just a plug and play. So first, we know that our pool is 55,000 gallons. So go ahead and write that in that section. Next, we see that after testing, our results are 1 part per million, and we need to get to 3. So the difference between 1 and 3 is, you guessed it, 2 parts per million. Now, the question itself tells us what chemical we're using. The answer to that is calcium hypochlorite. So over on page 6, I am going to be looking at my to increase chlorine section. I'm going to find my calcium hypochlorite addition rate, and I'll see it's at 2 ounces. So I am going to plug that 2 ounces into my chemical section. Now, like I said at the beginning, you need to remember that you have to convert all of these. And as we can see, that 2 ounces is a dry measurement. It's a dry measurement. So our conversion rate here is going to be 16. So we are simply going to take 55,000 divided by 10,000 times 2 divided by 16. If you do the math correctly, you should come out to 1.375 pounds. If you had issues with this, again, simply just rewind the video and listen to the explanation again. Now let's move on to our second example question. It says you find your calcium hardness is 65 parts per million in your 75,000 gallon pool. How many pounds of calcium chloride would you need to add to raise the level to 225? Let's do it exactly like we did the first one. First, let's plug in our pool volume, which is 75,000 gallons. Now we need to figure out what our parts per million change is. We want to get up to 225, and we're at 65. The best way to go about this is take 225 minus 65 And whatever you have left over is what your change needs to be. 225 minus 65 gives you 160 parts per million change. The question asks us what we need or how many pounds we need to add of calcium chloride. So it's told us our chemical. We look over on page 6. We find our to increase calcium hardness section. We find calcium chloride at 1.92 ounces as our addition rate. And then finally, we need to add that conversion in. And since it's a dry measurement, we are going to be dividing by 16. Now, let's do the math all the way across again. 75,000 divided by 10,000 times 160 times 1.92 ounces divided by 16. If you do the math correctly, you should get 144 pounds. Now again, if you are confused, I recommend that you re-listen to both of these sections on chemical adjustment and the explanation, and review the video as much as you need to. That's the beauty of this online portion, is you have the ability to go back, rewind, and listen to it and redo it until it really starts to sink in. So next, let's talk about our combined chlorine problems. Now, we don't like combined chlorine in our water. If you'll recall, combined chlorine is a bad thing that we have in our pools. It will cause a bunch of different issues. It'll cause pulmonary issues. It'll cause eye and skin irritation. We want to get rid of it as much as we possibly can. There's a few different ways to reduce those chloramines. And as you can see on the slides, these are all of our different choices. The biggest one that we're going to be using in the modern day is using something called potassium monoprosulfate. Or, as you can see on there, it's non-chlorine, and unfortunately my slide is improperly formatted again, but it is non-chlorine shock. Potassium monoprosulfate is non-chlorine shock. This is the product that you're going to want to have on hand in order to properly eliminate your combined chlorine or your chloramine reduction. But during the exam, they are actually going to walk you through what's called a breakpoint chlorination. Now, the process behind breakpoint chlorination is fairly interesting. It can be complex, so I will repeat it just to make sure that it sinks in as much as possible. But essentially what we've looked at is science has determined that if I raise my free chlorine level, my good chlorine level, 10 times higher than my bad chlorine level or my combined chlorine level, that heightened free good chlorine level will actually end up eliminating my bad combined chlorine level. I'll say it again. If I raise my free chlorine level 10 times higher than my combined chlorine level, that will eliminate my combined chlorine out of my pool. This is the process of breakpoint chlorination. Now, as we see on the first point in our slide, once our combined chlorine reaches 0.5 parts per million reading or more, that's when it's time to actually do something. It's once we hit 0.5 parts per million or more that it's time to do something. And what we're going to do is a breakpoint formula. You're going to find our breakpoint information on page 8 and 9 in your workbook. Go ahead and turn with me there now. Page 8 and 9 in your workbook. On page 8, you're going to see our example question. Below the example question, you're going to see our chlorine increases that will be used for our test questions as well as the questions used on the actual exam itself. Over on page 9, you are going to see the formula that looks exactly like the formula that you see on the screen. Now, what we're going to do is we're going to walk through these steps before we actually perform the formula itself. Now, step 1, TC minus FC equals CC. Total chlorine minus free chlorine equals combined chlorine. We are doing this step simply because the majority of our test kits cannot directly test for combined chlorine. So we're having to figure that out on our own. And like we talked about earlier in the chapter, we're simply going to do that by taking our total chlorine, subtracting our free chlorine, and whatever's left over is our combined chlorine. Now on step 2, you're going to see that we drop that combined chlorine down to the beginning of step 2 and we multiply it by 10. This is going to show us our breakpoint chlorine number that we need to achieve. Remember, if we raise our free chlorine 10 times higher than our combined chlorine, it will eliminate that combined chlorine. Step 2 is helping us to see what level we need to get our free chlorine up to in order to eliminate our combined chlorine. Once we determine that number, we'll drop it to the beginning of step 3. On step 3, you will see our breakpoint chlorination minus free chlorine level. Now, what we're doing in step 3 here is we're taking our breakpoint chlorine and subtracting our free chlorine in order to see how much actual chlorine we need to get to in order to achieve our breakpoint chlorine level. There's no reason to add more chlorine than we already need, and we've already got some chlorine in that pool, so let's use it to our advantage. That's essentially what we're looking at on step 3. Then finally, you look at step 4, and it's a simple chemical adjustment question. So now that we've walked through this, let's go ahead and plug it in. First, your total chlorine is 1.5 parts per million, and your free chlorine is 1 part per million. How many gallons of sodium hypochlorite will you need to add to your 68,000 gallon pool to achieve breakpoint chlorine? Now, the question we just heard found on page 8 of your workbook gives us all of the answers that we need. So first it tells us our chlorine, our total chlorine, is 1.5 parts per million. Let's plug that into our formula. Next, the free chlorine is 1 part per million. Now let's take 1.5 minus 1, which gives you 0.5. Then we take that 0.5, drop it down to the beginning of step 2. And if we take 0.5 times 10, that's going to give us 5 parts per million. Our breakpoint chlorine number needs to be at 5 parts per million. So now we drop that 5 parts per million down to the beginning of step 3, and we also subtract our free chlorine, which, as we remember, is 1. So we take 5 minus 1 gives us 4. Now we drop that 4 down into the ppm change section on step 4, and we add all of our numbers accordingly. We add in our pool volume, which is 68,000. We add our chemical. If we look on our chemical section over on page 8, we're going to see that this requires a 10.7 fluid ounce conversion. 10.7 fluid ounce addition rate because we are using sodium hypochlorite. Now, I got tripped up on my words conversion because I got the cart ahead of the horse to remind you that this is a fluid ounce. It's a fluid ounce. So if you look on page 9 at the bottom, you're going to see that our conversion rate is 128. Look on the bottom of page 9 and find your conversion, which is 128. So now we are going to take 68,000 divided by 10,000 times 4 times 10.7 divided by 128. And your answer, if you got it correct, should be 2.27 gallons. Again, if you need to rewind and rewatch this as many times as you need, don't hesitate to do so. Chapter 6, Water Balance. Chapter 6. Now, when we hear the words water balance, for those of us who have been in the industry for a while, sometimes you may just think the balance of chlorine and pH and making sure that those are good levels. But in reality, what we're looking at is the correct ratio of mineral content and pH that prevents water from becoming corrosive or scale forming. So essentially what we're looking at is a proper balance of all of the minerals and pH inside of our water to prevent it from becoming either corrosive or scaling. Now, the balance factors that we're going to be discussing in this chapter are pH, total alkalinity, calcium hardness, temperature, and total dissolved solids. So let's go ahead and look at each one of these individually. The first one is going to be pH. Now, pH has the largest impact on our water's balance as well as our user's comfort. Now, as we can see on our scale, at the 0 point, we're acidic. At the 14 point, We're completely basic. This reminds us, hopefully, of our middle school or early high school chemistry classes. Where we're falling is somewhere between the 7.0 and 7.9 section of neutral. We have been given the operating acceptable parameters of a pH between 7.2 and 7.8. Again, our acceptable operational parameters are 7.2 to 7.8. Anything below this could potentially get us shut down. Anything above this could also potentially get us shut down. Now let's zero in a little further towards the ideal range. The ideal range is 7.4 to 7.6. And if we narrow this down even further, we'll see that truly perfect is 7.5, just like we talked about in the previous chapter. Now, if our chemicals or our pH reading is out of balance, we're going to need to add chemicals in order to get it back into balance. So let's say our pH goes too high. If we need to decrease our pH, we are going to add a muriatic acid. This is our liquid option for decreasing the pH. If we want to add a solid, we can add sodium bisulfate. If we want to, we can also add carbon dioxide gas by injecting it directly into the water, and it will decrease effectively our pH. Now, to increase pH, you are going to be using soda ash, which is a dry chemical. If you're using a liquid feed system, you can use sodium hydroxide. You also have the options of using borates or air if you are using a gas system. That's right, soda ash, sodium hydroxide, borates, and injecting simple air into your pool will increase your pH. It's called oxygenation, is the process for increasing pH by using air. Now remember, we can add these acids and bases directly to the pool as long as that pool is closed and remains so until the chemicals are completely dissolved and dispersed. Until the chemicals are completely dissolved and dispersed. Make sure that we are watching this because in your local jurisdiction, your local municipality, they may have requirements for what dissolved and dispersed means. For instance, here in Denver County in Colorado, where we're based, the Tri-County Health Department defines dissolved and dispersed as one full turnover. And if we remember from earlier in the class, one full turnover equals 6 hours of time. So with that, it's good for us to maybe think about switching our chemical addition times from early in the morning before the pool closes to later on at night after the pool is closed to allow that 6-hour turnover rate to properly dissolve and disperse according to your local health department requirements. But remember, you can only add them directly to the pool as long as the pool is closed and there's nobody in it. Total alkalinity. Now, total alkalinity is essentially a buffer for our pH. As long as our alkalinity is in order, our pH will be a lot more pliable, a lot more able to bend to our desires. So as long as our alkalinity is in line, pH is going to obey our rules a little bit more. Now, what are those parameters looking like? Well, ideally, we want to have an alkalinity that's between 80 and 120 parts per million. 80 to 120 parts per million. Now, if we go low on our alkalinity scale, we're going to experience something called pH bounce. If we're approaching levels below 60 parts per million, we're going to notice that every single time we test our pH, it's going to be out of whack. First time it's going to be 7.2, next time we test it is going to be 7.5, next time we test it, it'll be 7.1, all over the place with pH bounce. Now, conversely, on the high side, if we start reaching numbers around 180 parts per million, we'll experience something called pH lock. Now, pH lock is a concept where as your alkalinity rises, so does your pH. And you won't be able to lower that pH until you address your alkalinity problems. So we need to make sure that we're keeping our alkalinity in proper parameters in order to keep our pH under control as well. Now, if my alkalinity gets too low, I'm going to increase it by using something called sodium bicarbonate or industrial grade baking soda. To increase our alkalinity, we use sodium bicarbonate. Now, to decrease our alkalinity, we're going to use either muriatic acid or sodium bisulfate. Now, this is a little bit confusing because we just learned that to lower our pH, we're also going to use muriatic acid. Now, for the sake of keeping this as simple as possible, I'm not going to go into the science behind it at this point. If you want to know more about that, write it down and I can talk about it during the Q&A session. But essentially what we want to think about is lower your alkalinity first and then adjust your pH accordingly. As long as you're lowering your alkalinity first using muriatic acid and then raising or balancing your pH after the fact, your pH is going to take a lot less coaxing when it comes to chemical adjustment if your alkalinity is in the right place. So again, like I said, for the sake of simplicity, we will say make sure that you lower your alkalinity first and then adjust your pH back to where it needs to be after adding that muriatic acid to lower the alkalinity. Now, next on our list is calcium hardness. Think about calcium hardness as hard water or soft water. Hard water means there's too much calcium hardness in the water. Soft water means there's not enough calcium hardness in our water. So we don't want either of them necessarily because low calcium hardness equals acidic or corrosive water. High calcium water equals scaling water. So what is the ideal? As you can see on the slide here, it's 2 to 400 parts per million. 2 to 400 parts per million. Now, you can go as low as 150 parts per million in pools and up to 1,000 parts per million in those pools, but you don't necessarily want to go either one of those routes. Making sure you've got 2 to 400 parts is going to make sure that your balance stays as perfect and ideal as possible. The lower you go on the calcium hardness scale, the more likely you're going to see corrosion happening in the water. That means etching of the pool surfaces. The higher you go on that scale, the more likely you're going to see scale building up. Now, a lot of times this scale doesn't just look like chalk, like we normally see with scaling. Instead, what it's going to do is it's going to adhere itself to the surface of your pool, and sometimes we'll make almost little harsh pinpoints of calcium buildup, almost like little stalactites growing on the side of your pool, and when you brush up against it, it can be extremely abrasive to the skin. So again, making sure that we're in good balance is absolutely crucial. Now, one last point about calcium hardness levels. With our hot tubs, we're actually looking to be between about 150 and 250 parts per million. The reason behind this is because calcium loves cold water, and it doesn't really work well to have higher calcium levels in warm water. The reason why is because calcium in warm water tends to deposit a lot more easily. So making sure that we keep those levels low in our hot tubs between 150 and 250 is going to prevent any sort of mass scale depositing going on in there. Now, to raise your calcium levels, you're going to simply add what we did earlier in the chemical adjustment section, and we're going to add 77% calcium chloride. To increase your calcium hardness, you're going to add 77% calcium chloride. It's that Dow flake. Dow flake allows it to go into a solution a lot faster. Now, to decrease your calcium hardness, it's really difficult. It's really difficult, time-consuming, and, most importantly, very expensive. So the best way to decrease your calcium hardness instead of using something like an industrial-grade softener is to simply replace your water. Once your calcium levels get to the point where they're too high, you can simply dump and refill with new, fresh water, and that should lower your calcium hardness levels. Now let's talk about temperature. With temperature, ideally you're going to see in the book that temperature, and excuse my slide because for some reason it went crazy on me, you're going to see ideally we're looking at 80 degrees according to the book. Now personally, I think that is frigid cold water. I prefer something around, say, 85 degrees. But the book does remind us that for every 1 degree over 80, energy costs are going to increase approximately 10%. Now here's something that I want you to consider though. is when it comes to our overall water balance, temperature plays a really small part of that. So small, in fact, that I highly recommend that instead of going off of a balance factor, instead give your swimmers, your guests, the temperature that they're looking for. If they want to swim in an 85-degree pool, give them an 85-degree pool. Yes, this will increase your energy costs, but as long as you can build that into the mass cost of the patronage of your facility, people aren't going to notice that cost raise, and they're also going to be very, very thankful that you have a pool that they're willing to swim in and able to swim in because it's warm enough. So again, like I said, this really comes down to a marketing tactic more so than an actual scientific balance. So give your swimmers what they want, and they'll thank you for it in reviews on TripAdvisor, Yelp, whatever it may be. Now let's talk about total dissolved solids. Now, total dissolved solids are the total weight of all soluble matter in the water. This comes from things like bather waste, whether it's sweat, urine, feces, whatever it may be coming off of people's bodies, disinfectant byproducts, specialty chemicals, algicides, dirt and debris, anything that was once a physical matter that fell into your water and dissolved to the point where we can no longer see it is part of this TDS measurement. We also call this the age of our pool, simply because as time goes on, our evaporation process is going to take the pure water and it's going to leave our solids behind. So over time, you're going to notice this buildup of TDS, or total dissolved solids, causes a tired look inside of your water. It may not look cloudy, it won't look hazy, it just looks dull. It doesn't sparkle the way that it used to. In fact, high TDS levels can also lead to a very unpleasant salty taste. Now, thankfully, we don't have to go off of a taste test to see how high our TDS levels are. You can go to your local supplier or jump online with some supplier like Amazon even and buy a fairly affordable TDS meter. In fact, I highly recommend that this be part of the arsenal of your tools for understanding the health of your swimming pool. So making sure we keep those high TDS levels down is absolutely crucial. So ideally, what we want to see inside of our swimming pools is no higher than 1,000 parts per million over our starting number. The way you get that starting TDS, well, there's a couple of possibilities to do this. Possibility number one is once you fill up that pool initially, you check that TDS. Whatever that TDS reads, that is your starting TDS. Now, if you've come into a property that already has a full pool, you can't really figure out by dipping inside the pool what that starting TDS is because the water's been in there for a while. So instead, what you're going to want to do is make sure that you check your tap water. Tap water is going to give you a great insight into what your starting TDS was when that pool first filled. So now that we have that number, we're looking to go 1,000 parts per million over that starting number. And once it goes 1,000 parts per million above that, we're going to dump and refill our water with fresh, good, crystal clear water. With hot tubs, we're looking at 1,500 parts per million over start. Now for us at our fitness centers, these are going to raise in our spas up to that 1,500 parts per million on a busy day, a Friday, a Saturday, because the plain and simple fact is when people get into our hot tubs, they're shedding off everything that they bring in there because they're sweating it out, they're urinating. Again, I don't mean to be graphic, but this is just the reality, especially at those fitness centers. Now, it's also not an implication that you as maintenance personnel at these properties are doing a bad job. By no means is that the case. What we're looking at is that our bathers are not taking proactivity in mind and instead are just allowing all of that to spread out into the general masses inside of that hot tub. So check your TDS levels regularly, especially in the higher used hot tub areas in places like recreation centers, fitness centers, so on and so forth. Again, making sure that we keep those TDS levels down is also going to prevent the rise of something called galvanic corrosion. Now, you might want to write this down as I talk about it. This first point is galvanic corrosion is signaled by a discoloration of metal parts in the water. Again, I highly recommend that you write that one down. It's signaled by discoloration of metal parts in the water. If you want to see a great example of this, look inside your handbook at page 68, and you'll see a picture of a blackened ladder on there. Now what happens is the high TDS levels above 2,000 parts per million has caused the dissimilar metals that exist inside of that pool to bond together and stain out on that ladder. Now again, sometimes you'll see just a crazy blackening of that ladder, or sometimes you'll see this take the shape of weird funky looking rust. So we really don't want either of those colors inside of our pool. Instead, we just want to make sure that we are keeping our total dissolved solids as low as we possibly can. Now, all of these readings lead up to us being able to understand what our saturation index is. Now, in a nutshell, the simplest way to understand the saturation index is the saturation index is a test that's been given to us by scientists to help us figure out if our water is either corrosive, scaling, or perfectly balanced. Go ahead and look on page 69 of your books, and what you're going to see is how we calculate our saturation index. The way that we calculate this saturation index, as you can see on our slides, is we're going to test our pH, and then we're going to add a temperature factor that represents our actual temperature. Then we're going to add a calcium factor that represents the reading of our calcium. We're going to add an alkalinity factor that represents our alkalinity reading, and then we're going to subtract a TDS factor. Once we do this, we should end up with a number between negative 0.3 and positive 0.3. As long as we land somewhere within these parameters, then we are considered balanced. Anywhere below that number is corrosive. Anywhere above that parameter is scaling. So let's go ahead and explore this inside of our workbooks. Go ahead and turn over to page 4 and 5 in your workbook right now. Now, on page 4, you're going to see our saturation index factors. Like I said, these factors are going to represent the readings that we actually have inside of our pools. Then on page 5, we're going to see our example question, and we're going to see our saturation index calculator. What you're going to see is in the first column there, you're going to see our value section. This is where we write in all of the actual readings that we're getting from our swimming pools. The next column is going to be our factors section. This is where we write in the factor that represents our number that we read inside of our pool. Now, one big thing to remember is our pH does not have a factor. According to our saturation index, our pH is simply put into our factor section as it's measured. For instance, if it's 7.2 in the value section, the factor is 7.2. If it's 7.4 in the value section, the factor is 7.4. Now let's go ahead and read our question, and as I read the question, I would like for you to fill in the value section as we go. It says, after a complete test of your 175,000 gallon pool, you find that your temperature is 84 degrees, your pH is 7.8, your calcium hardness is 250 parts per million, your total alkalinity is 125 parts per million, and your total dissolved solids are 800 parts per million. What is your saturation index? So now that we have all of our values filled in, let's figure out our corresponding factors. For our pH, we already know what this factor is because our pH is as measured. So we take that 7.8 and we simply shift it over to our factor as 7.8. Now, every other number on our chart is going to have a factor that represents our actual number. That factor can be found on page 4 of your workbook. So first, let's check our temperature. Our actual temperature is 84 degrees. I go over to the temperature factor in my workbook. I hover down to 84 degrees, and I find in the darkened section that my factor for that 84 degrees is 0.7. So I'm going to plug into my factor section 0.7. With my calcium hardness, I'm going to do the exact same thing. I'm going to look for 250 parts per million, and then I'm going to notice that that 250 parts per million has a 2.0 factor. With my alkalinity, I find 125 parts per million in my lighter side, and my darkened portion, my factor side, says that the factor for that alkalinity is 2.1. So now we're going to add those factors all together. We're going to take 7.8 plus 0.7 plus 2.0 plus 2.1, and that's going to give us a subtotal of 12.6. Now we still have our TDS factor. Now if you look at the bottom of page 4 on your workbook, you're going to see our TDS factors. If your TDS is less than 1,000 parts per million, you're going to put a negative 12.1 in that section. If it's greater than 1,000 parts per million, you're going to put a negative 12.2. Now, as we can see, 800 is less than 1,000, so we're going to be putting a negative 12.1 in that section. Now, notice that we already have the negative symbol in there, so you don't have to place it yourself. And now all we have to do is take our subtotal minus our TDS factor. So we take 12.6 and subtract 12.1, which leaves us with a remaining positive 0.5. Now we need to ask ourselves, are we scaling, are we corrosive, or are we balanced? Now if we remember that we need to fall somewhere in between negative 0.3 and positive 0.3, we can find that this saturation index indicates that we are in fact scaling. Now what I can look at here is that my pH is very high. So I can remember that it has the greatest impact on my overall balance. So I'm going to attack that pH first and foremost. If I drop that pH from 7.8 to 7.4, which still lands us in our ideal zone when it comes to pH, I will take that 0.5 and subtract 0.4 from it as well, which leaves me with a 0.1 index. That's almost nearly perfect. So again, this is the insight that our saturation index can give us. Don't forget to write down any questions that you have in this chapter so we can go over it during the Q&A period. Chapter 8, Chemical Testing. Chapter 8, Chemical Testing. Now the question is, what are we testing for? Well, we're testing for everything that we've explored so far. We're testing for disinfectant, pH levels, total alkalinity, calcium hardness, cyanuric acid, and total dissolved solids levels. Now there's a few general testing methods that we use out there. The first is our color metric. Now for anybody who's used the Taylor test kit, you will be very familiar with the color metric type test. Now with the color metric type test, this is where you add your reagents into that clear tube, shake it around, and check it for accuracy or comparison to what you see on the tube itself. You'll find this picture on page 87. Now, colorimetric is our most common type of test, but believe it or not, it is our most inaccurate. The reason why it's inaccurate is because of the actual comparison of the color. It's so very subjective that everybody has a different opinion on what that shade of a color may be. This is extremely, extremely unreliable and very, very inaccurate. So I recommend that we avoid colorimetric as much as possible. Now the next one on our list is the titrometric type test. This is a test where a color change occurs. This is what you'll see with your alkalinity test or your calcium hardness test if you're using the Taylor test kit. It changes from one color to the next, and once that change comes, you do the math multiplication and it tells you exactly what your reading is. This is a little bit more objective instead of subjective like colorimetric. Now the big thing to remember is you can actually get a test for chlorine that is a titrometric type test. Now one thing that I would write down for the test in your notes section is what you see on the screen. I would write down that FAS stands for ferrous ammonium sulfate, and it's a titrometric type test. The chlorine test that is a titrometric test is the FAS DPD. This is where that FAS that you see on the screen comes from, and it's a titrometric type test. Again, titrometric means it goes from one color to another color, so you have more of an objective view on what your actual readings are. Now, you can add this to your Taylor test kit for about $20, which is great. But again, I don't recommend it simply because what we're looking at is an objective view with our pH still. Our pH remains a colorimetric type test in that Taylor test kit. And when we talk about frequency of testing, you're going to see that we're going to be testing our pH as often as we're testing our disinfectant. So, from my personal opinion as your instructor, I highly recommend that we get away from that Taylor test kit if at all possible. Our next test that we're looking at is the turbidimetric test, or a water clarity. Turbidity is a fancy way of saying is the water cloudy, or the level of cloudiness of that water or that test. We use a turbidimetric test to measure things like cyanuric acid. And then finally, we have our electronic tests. Things like our TDS meters are going to be our electronic readings. Now, like I said earlier at the top of the list, our DPD or colorimetric test, not recommended. The FAS DPD is more recommended, but I still feel like it's going to leave you at a deficit. But our photometric test kit is going to be exactly where you want to land. That photometric test, we see an example of that on this slide in front of you in the bottom right-hand corner. This one is the Lamotte Color Q Pro 7. The Lamotte Color Q Pro 7. I highly recommend that you look into this test kit. As I said, it's a photometric type test kit. So what we do is we take a vial, we add our reagent, we slide it into that blue device in the middle of the test kit, we push the buttons on top, and in about an eighth of a second, it will send back a digital reading of exactly what that test reading is inside of that vial in the photometric test kit. You take that vial out, add the next vial that has your next reagent mixture in it, push the button again. In a split second, it's going to spit out the new number, and you're just going to write these down as you go. This takes out any of the human element. Now, there will be some that come and say, well, this isn't 100% accurate. And they're absolutely right. This weighs in between 92 and 96% accurate. But the colorimetric test kit is roughly 30% accurate, maybe sometimes 10% accurate. For those who are actually colorblind out there, it's 0% accurate. So I would prefer a 92 to 96% accuracy on the test kit than the subjective nature of something like a colorimetric test kit. Now, if you want to compare these, you can go to the next bump up. The next bump up is going to be the IDIP test. With the IDIP test, you're looking at about $500 investment. That's pretty pricey, especially when you compare it with the Lamotte Color Q Pro 7. Right now, if you look online, you're going to be able to get this Lamotte Color Q Pro 7 for about $140. That's a huge difference between the IDIP test. Next, if you want to go above that, you can get the Palin test. Now, the Palin test is going to give you about a 98% accuracy. So on the best side, you're going to get a 2% more accuracy level. You're also going to be paying about $1,500 for this test kit. And then above that, we've got the Hawk test, weighing in at around $3,000. The Hawk test is 98% effective. 98% accuracy compared to 96% accuracy at a price that is literally thousands of dollars cheaper puts it into perspective a little bit more and helps us understand that the Lamotte Color Q Pro 7 is probably the best kit that we have in the price range. Now, I want to be very clear. I'm not getting paid by Lamotte to tell you this. We don't take any sort of sales. We don't take any sort of commission on any of these items that we're talking about in class. What we've done is we've researched everything for you so you don't have to take all of the time to do it yourself. If you research yourself and find something better, by all means use it. But in our experience, these are the devices that we found that have been most successful for us. So again, when it comes to test kits, if you can throw out that DPD test kit, i.e. the Taylor test kit, do so and replace it with the Lamotte Color Q Pro 7. Now remember, when we're collecting our samples, we want to go 18 inches below the surface and away from any return lines. This is going to give us our most unadulterated and accurate read of what the actual pool chemicals are reading. 18 inches below the surface and away from any return lines. Now let's talk about our testing frequencies. Now, as you can see here on the screen, we have the Colorado State Code testing requirements. They have daily, weekly, and monthly testing frequencies. The reason why I brought this one up is because it is very well laid out. Not all of your codes are going to be well laid out like this, but what I recommend is after this session is over, find a copy of your state and local code and see what they require when it comes to testing frequencies. Some will require that you test more frequently than the Colorado State Code. For instance, there's some local municipalities that require 4 daily testings of things like disinfectant, pH, and your ORP, or your oxidation reduction potential, which is for our automatic controllers. Some will require less. I personally think that any less than 3 leaves you open for liability. So if your local code is written that you only need to do 1 or 2, I would err on the side of caution and go with 3 to 4 tests every single day, simply because that's going to protect you in a liability situation. So again, being more strict than more lax on something like this is always going to benefit you. And like I said, be sure that you go back and check your state or local code to see exactly what tests are required. If you can't find it, if it's not written, if you don't have a code, always go back to the Model Aquatic Health Code. Again, on our website, you'll be able to find that in our Codes and Resources section. You click on the Codes and Resources tab. That will lead you over to the page where you can find a link over to a free download of that Model Aquatic Health Code, and it will walk you through absolutely all of the testing requirements that are recommended as a standard across the world. Now, another thing that we need to talk about here is the record keeping itself on your testing frequency. Make sure that you are marking these down in a formal way. On page 241 of the book, you're actually going to find a template chemical log right there. You're more than welcome to Xerox that and use it for every single test that you take. Make sure that you're filling it out comprehensively with what you're required to fill out, because that is going to be your proof that you did what you were supposed to do if there ever is an incident. When there is an incident, the first thing that they're going to ask is for your test records. So make sure that you have those on hand and available for them to be able to look at. One thing that I will also say, though, is the paper world is kind of going away, for better or for worse. We're moving over more towards digital platforms. And the thing that's nice about digital platforms is they really are more well integrated and more helpful to you as an operator. There is one that we at Pool Training Academy highly recommend, and it's called Facility Manager. Now let's go ahead and take a little bit of time here to look at Facility Manager and see exactly how it might help you out. This is put together by a company called Councilman Huntsaker. Now what this app does is it records all of your tests for you digitally. It's web-based, so you can access it on a cell phone. You can access it from a tablet, an iPad. You can access it from your computer. Wherever you need to, you can access the Facility Manager Pool Test app. The thing that's really nice is you plug all the numbers in, and it shows you exactly what your readings are and what chemicals you need to add to your pool or your hot tub to perfectly balance that pool. The best part about this is it's affordable. It's about $150 a year, which equals out to about $12.50 a month. Now, I've done a lot of research on apps for pool chemicals, and this one, for its robust nature, is absolutely unbeatable with that price. The nice thing is that price applies per facility. So that means that you, at your property, if you have a pool and a hot tub, you're still only paying $12.50 a month to do your tests and records on both of those bodies of water. So again, like I said, this is a great value, and it's the Pool and Hot Tub Alliance approved. The PTA approves of this Facility Manager app. In fact, it's the only app out there that gets the seal of approval from the PTA. Now, a couple of notes to take. With our disinfection testing, we've got our good old-fashioned multi-test test strips. We are not allowed to use these in our industry. They are not allowed. They're not code. For a couple of reasons. First, we can see it's colorimetric. We're comparing colors again, which is going to give us an inaccurate read. Secondly, if you open up this tube and one single drop of water gets inside the tube, it will compromise all of the tests inside of that tube. So again, because of the finicky, inaccurate nature of these multi-test test strips, we're no longer allowed to use them. Now, one thing that I will say is I don't know if it's a bad idea when you're traveling, if you have a family or something like that, to take these along with you, and before you take a swim, get into that hot tub, do just a little ninja dip with one of these test strips and see what those chlorine or bromine levels are reading. If those levels are satisfactory to what you've learned in this class, feel free to let the kids swim. If they aren't, well, maybe go putt-putt golfing instead. But again, anecdotally, that's the only way that these are recommended is if we use them for our own personal use, not a commercial use. Now, a couple of things to keep in mind also when it comes to oxidation reduction potential is this is our automation. This is our automation. Now, for anybody who's not using ORP, or anybody who is using ORP for that matter, write that underlined bullet point down. ORP is measured in millivolts. It's measured in millivolts. Essentially, what an ORP reader does is it's got a couple of probes that sit inside your water. These probes are looking for electron exchange. Electrons exchange more highly in chlorinated water than they do in lower chlorinated water. So these probes, when they read higher electron exchange, they say, oh, there's a lot of chlorine in this pool. We're good to go. But when it tests and it doesn't see that electron exchange, it says, I need to burst some chlorine in here in order to be able to get those chlorine levels up. So it does just that. It reads again. Once it reads that electron exchange, it cools off and says, okay, I've done my job. If we're using cyanuric acid in a pool that has an ORP reader, remember that cyanuric acid is going to create a protective shell around our chlorine, and as a result, it's going to hinder those probes from reading that electron exchange. So as a result, it's going to give you inaccurate reads on your controller. Again, another downfall of cyanuric acid, and why we at Pool Training Academy highly recommend that you limit at the point of not using it anymore at your properties, if at all possible. A couple of notes to take before we finish this chapter. With our pH testing, we test that using something called phenol red. Write that down. Again, we test our pH using phenol red. It will only give correct results between 6.8 and 8.4. Anything below 6.8, it's going to turn into like a highlighter color, that greenish yellow. Above 8.4, it's going to just stay that dark red, maroon color, and you're not going to be able to get an accurate read. Now, finally, let's talk about our false test readings. With our chlorine, if we're using that old Taylor test kit, our reagent is going to just straight up bleach out if our chlorine's above 10 parts per million. You're going to drop it inside the color comparator tube. It's going to hit that water, swirl pink, and then disappear completely. For us, we might think, oh, we must not have any chlorine at all. But in reality, it's the exact opposite. Now, to figure out if that's the case, you're going to want to test your total alkalinity. If that end result turns yellow, that means that your chlorine levels are above 10 parts per million. This concludes this chapter. Make sure that you take some time to write down any questions that came up so we can answer those during our question and answer period. Chapter 9, Chemical Feed and Control. Now, one of the big things to remember that we touched on earlier is when you're adding chemicals to your pool physically, make sure that you never grab a bucket, put chemicals in, and then add water to that bucket. That could equal out to be a disastrous result, ending in quite literally an explosion. So make sure that you first grab a bucket, fill it with pool water, and then add your chemical into that bucket of water. Also, make sure that when you're adding chemicals directly to the pool, inside of that bucket, you're never creating a chemical cocktail. Never mix chemicals in a bucket at the same time. That chemical cocktail can end up gassing out and potentially causing a fatal accident to occur. Also, this should go without saying, but unfortunately, in the world in which we live, I still have to say it, but never siphon chemicals by mouth. This is simply a bad idea, so don't do it. Also, make sure that you're never flushing those excess chemicals down your toilets or your drains. The EPA, I swear, has somebody down inside the sewers watching for when we do this, and they will be able to find you, and they won't hesitate to slap a hefty fine on a property for doing that. Also, when possible, make sure that you're always using a clean scoop for each one of your chemicals. Make sure that you're segregating those to each one of those chemicals so you don't have any cross-contamination issues. Another big deal is to make sure that your chemicals stay in their original containers. Now, I get it. Trust me, I understand this. We don't want to keep those bags of soda ash, for instance, just sitting around because they are made out of paper, the bags themselves. When they sit in our damp environments, those bags tend to go bad, so we want to put those inside a bucket of some sort. You are allowed to do that, but whatever you do, make sure that you're not just dumping that chemical from the bag into an unmarked Home Depot bucket or an old chlorine bucket. Instead, what you need to do is you need to grab the entire bag with the chemical inside it and put the bag and chemical inside the bucket itself. Failure to do this can actually result in what's called a potential terrorist threat, a threat to U.S. national security. I know it sounds way overboard, but because of terroristic attacks that have happened in the past, they no longer see this as just a minor flub. It's become a fairly big issue. So make sure that when you're protecting those chemicals, you're putting the entire bag with the chemicals inside the bag in the bucket. Always a great idea to cover your chemicals as well. You don't want any of those chemicals gassing out and causing horrific corrosion inside your facility or getting inside of your lungs as well. Now, if there ever is a spill, make sure that you jump directly to your SDS sheet. Some of you may remember these as the MSDS, but now all manufacturers have formally moved over to the SDS instead. So make sure that you are cleaning the spills according to what your SDS sheet indicates. Now, we've already talked about the addition by dilution. This is where you add that chemical to a bucket of water, not vice versa. Make sure you're stirring with a non-combustible material and never your hand. Something like a stick is preferable when it comes to certain chemicals. Again, make sure that you're evenly distributing that chemical around the deepest end of the pool and let it dissolve and disperse as required by your local health department. Once you're done, make sure you rinse and store the bucket according to the product label instructions for the storing of those chemical components like this. Now let's talk about chemical feeders. Mechanical feeders, there's two different types. There's the liquid solution feeder, which is our peristaltic pumps. Now, with these peristaltic pumps, it's a roller that squeezes a flexible tube inside. That flexible tube on the inside of this device will become compromised over a short period of time, especially when you're adding something like muriatic acid with a peristaltic pump. So what I highly recommend is pull the cover off of that peristaltic pump every couple of months and check the integrity of that inner tube. If it ever feels like the outer tube is separated from the inner tube by a layer of jelly, you know it's time to change that tube very, very quickly. Make sure that you've got extras on hand so you can do that. Because if one of these tubes tears and breaks inside there, leaks that acid or whatever caustic chemical it may be inside this peristaltic pump, it can cause disastrous results and require you to buy a new peristaltic pump, which can sometimes run you about $200 on each one of these. So make sure that you're checking those regularly. Also, make sure that you're installing these below eye level. Ideally, we want these below the waist, around the knee level. But that's not always the way it gets installed. The reason why we want to install these is because if we ever have any breaks in our lines and that chemical of whatever it may be is shooting across the pump room like an unmitigated super soaker, you don't want that stream at eye level, because the last time I checked, eyes getting filled with muriatic acid is a very bad thing at your property. So make sure that you lower these to prevent any issues like that from happening inside your pump room. Now, with our dry chemical feeders, make sure that we are following our dry chemical requirements. One of the things that you want to look at first and foremost, and write this down, is that erosion feeders are a type of dry chemical feeder. Erosion feeders are a type of dry chemical feeder. The way these work is you put those dry tabs, like the 3-inch trichlor, inside the tab tower. The water raises up around that inside the tab tower, and it dissolves those tabs. Once it erodes those tabs away, that chlorinated substance goes into the water, down into your line, and chlorinates your facility. Now, one of the big things that you'll notice here is that we never want to add granular chlorine to a tab feeder. Never add granular chlorine to a tab feeder. Our granular chlorine is volatile in that situation, and it's going to create a gigantic amount of pressure from the gas buildup inside that chemical feeder. As a result, within just a few seconds, you could have on your hands, quite literally, a chlorine gas-fueled PVC pipe bomb. You don't want that at your property. Best case scenario, it's going to pop the lid out and fill your pump room with chlorine gas. More likely case scenario is it's going to expand outwards, and we do not want to see that happen inside of our facilities. So make sure you're never adding granules to these tab towers like this. Also, make sure that you're looking and watching those control valves at the bottom of these units. The control valve is the little black device down there at the bottom that you can turn the volume up or down on your water source to your chemical feeder. After about 3 to 6 months, these tend to compromise and break, and as a result, you can see pretty catastrophic issues coming from this, where you're either under-chlorinating or over-chlorinating your facility on a consistent basis. So like I said, a pro tip says make sure that you are checking those control valves every couple of months to ensure that they're actually working. Now, one of the big things that we're going to see is our home study here. This is where we're going to take a break from our traditional lesson, and I want you to turn back over to page 10 in your workbooks, and you're going to see on page 10 of your workbooks, there are 10 questions there. These are practice questions for you. They're going to address all of the calculations that occur inside of our workbook and inside of the test. This is a chance to give you the opportunity just to get a little bit more practice. The more we practice, the more confident we're going to be with this math once we encounter it on the exam itself. Now, again, the good news is the exam math looks very similar to the exam math that we have on the test page, the home study page on page 10. So take about a half an hour's worth of time to do these. And then in the beginning of the next video, we're going to go over the answers to that home study. Again, with this chapter, make sure that you write down any questions that you may have to ask during our Q&A session.